First, I'm going to give another example where something called a transfer line. Again, this is going to use arguments on the events and parameters on the edges in kind of an interesting way. And then we're going to look at something called sim event listening. We've seen a number of examples of this idea of event listening. Going back to the Java class when we had action listeners, we had window listeners for looking at that, and all of that was in a graphical user interface context. So far, we've seen the property change listening for state variables. And what you'll see in the next computer assignment that I'm going to give you is how those property change listener idea can be used to collect statistics on our model. Okay, but that's off a little bit. This is the the fourth form of listening, and it's called sim event listening. And it's a way of taking our model and breaking it into smaller components and having the components interact through this listening thing. And so we're going to have yet another implementation of the multiple server queue that I call the simple server, because what it does is it actually breaks apart the multiple server queue into two of its pieces and has them listen to each other, or has one listen to the other, but we'll see what that's about. Okay, first the transfer line. And what the transfer line is it's a generalization of the tandem queue. Remember, last time we talked about how when we, instead of just having one bank of servers and then leaving the system, that in the tandem queue, the customers came, they got served by the first workstation, then they went to the second workstation, and then they were out. Which leads to the question, okay, what if there are 3? What if there are 4? What if there are n? So where this often comes into play is in certain types of fabrication processes where we have a sequence of events where will we have, oh, absolutely. Not a week is going to go by where we don't have a computer assignment. That will be, if you're eager to, actually, I was planning on posting that later today. It's all ready to go. I wanted to make sure that I covered this sim event listening because it's going to be using that. Okay, so the idea here, and this is motivated by certain types of fabrication processes where we have a series of workstations in a particular sequence. And each workstation is like a multiple server queue. Now, when you think of this too, you know, we often think of the assembly line. This isn't quite like an assembly line because in an assembly line, there really is no queue. In an assembly line, there's typically something, either a conveyor belt or in automotive, there are these huge, they're not conveyor belts, but they're these huge things that just periodically march the partially completed cars to the next workstation. And there you have like typically about a minute to perform whatever tasks you're going to be doing at that workstation, and then the thing moves on. Or if it's like on one of these conveyor belts, the conveyor belt is going at a certain speed and you basically have to do that. This is different. The idea here is that you have these, you know, jobs or customers, and we get processed by a series of these workstations in sequence. Something like a DMV is an example of that. Oftentimes when you check into a particular billet or something, when you first kind of get there, there might be this sequence of steps that you go through. In the vaccine that I got a few weeks ago over in DLI, again, there was a sequence of these things. I checked in, then there was another person that did the paperwork. There was yet another one after that. There was a queue to get the shot itself, and then there was another one another queue basically to wait for them to finish processing it and give me the card. So that was an example of this tandem, of this transfer line. It's called a transfer line because after you finish at each workstation, you get transferred to the next one. Okay, come on, there we go. All right. So, and hopefully you can kind of conceptualize this. So let's look at modeling this. So now we have, again, just like our arrival process like thing, we have the times between the arrival of jobs. You should be fairly familiar with that. Okay, now how many workstations we have? So here now we're parameterizing the number of workstations. So this generalizes the tandem queue, because with the tandem queue there were two, and we're stuck with two. For this, what's nice about this is that we can model any number of workstations with the same structure of the model. We just have to give it the right parameters. So what are the parameters? They're kind of similar to the ones for the multiple server queue. So for each workstation, it has, and we're going to call them machines because that's the motivation for this transfer line idea. So we're going to have a certain number of machines or servers, however we call them. The machines or servers could literally be machines, or they could be just some person. Doesn't matter. I mean, it's not that, people are obviously more important than machines, but just for the sake of the model, these are just bits on a computer, so they're not real people. No person was harmed in the making of this model. Okay, and we're going to use, because Java, like almost all modern computer languages, uses this silly zero-based indexing, we're going to call the first workstation 0 and the second 1, etc., up to n-1. Okay, so this is how many machines at each workstation. If you remember, for the tandem queue, we had a different number at each of the two workstations there. So here, again, we could have different numbers of machines. And furthermore, the service times at each workstation could be a different quantity, a different random variable, or even the same random variable with different parameters, or just some sequence that comes from somewhere. So these are our parameters. Our state variables, again, just kind of motivated by our multiple server queue, we're now making these arrays. So the number in the queue at station I is indexed by I. So we're going to have, basically it's like an array. So, and in fact, when we wind up implementing this, it's literally going to be an array. So the number in the queue at station I, we're going to begin empty and idle. And then the other state variable, which is also going to be an array, are going to be the number of available servers or machines at station I. And the initial value is going to be k sub I. Okay, so here's the event graph, and this is also in the reading. Okay, a couple things here. So let's just let's skip over this top part here. Let's just look at this. So here are our arrivals. This should be a very familiar structure. So run is going to schedule the first arrival at time t sub a. It's going to schedule each successive arrival with a delay. Okay. So now the arrival, though, is going to schedule an arrival with a 0 argument. Okay, so this arrival, this is the job arriving. This is the job arriving to the ith workstation. So when this arrival occurs, because it has the argument I, the first one is going to be arrival 0. And so that's going to increment Q0 to Q0 plus 1. And so if notice the condition, SI is bigger than 0. So if there's an available server at the very first one, if S0 is bigger than 0, it will schedule a start service, passing it this value I. Where did it get the I from? It got it from the argument. Then when start service at I occurs, start service at station I, it decrements the number of available servers at station I, decrements the number in queue at station I, and then schedules an end service event at station I with a delay given by the service time at station I. Then when end service occurs, it's going to now increment the number of available servers at station I. And then two things are going to happen. It needs to know there are two scheduling edges coming out. Okay, first, at that station, it says if there's anybody in the queue still at this station, then I need to start, I'll schedule a start service for them. Again, passing I, because that's at station I. But the next thing that happens is that the job moves to the next workstation. So how does it do that? Well, it schedules an arrival passing at I+1. So for the very first one, if I get an end service at station 0, then it will schedule an arrival at station 1. Now, it'll only do that if I is less than n-1. In other words, if, let's say, if I had 5 stations, n-1 is 4, so end service at station 4, with index 4 is going to be the end service at 4. 4 is not less than 4, and so it won't happen. Okay, do you see that? So see, structurally, though, change the color, come on. Why? Okay, structurally, this piece is almost identical to the multiple server queue. The exception is that they all have an argument and they pass that argument to the event that they schedule it for. Oops. Okay, so the thing is that even though this looks structurally exactly like the multiple server queue, it's not that we're just kind of putting an I everywhere. The I's have definite meaning and they have different semantic meanings. That is, the I's on the events are formal arguments, just like in a method. The I's in the boxes that schedule them are expressions that come from the arguments. And the thing to really, that makes a difference is this one right here. So when I end service at one station, I schedule an arrival at the next station. Only if I'm not at the last station. If I'm at the last station, I don't do that because there is no, if I have 5 stations, there is no station 5 because it's indexed just like Java arrays. Okay. Questions? Is that clear how that goes? And at some point, I'm going to have you, we're actually going to formulate models that use this concept and also implement. I think I'm going to have you actually implement the transfer line as I've outlined it here. Okay, next topic, and the final one for today. Let me make sure I have enough time here. Okay, sim event listener. This is a very, actually I didn't finish something on here. Sorry, let's go back. Let's go back to here. Oops. let's just look at this piece right here. This is that for loop that I mentioned before. And this is how state variables that are arrays are typically initialized. Remember, I said that strictly speaking, event graphs do not have the for loop available. So instead of the for loop, we use the event graph form of the for loop to initialize all of our state variables when they're arrays. So for scalar state variables, they get initialized in run. Here, we don't have any scalar state variables, so there's nothing there. However, if I have an array state variable, then this is the pattern that they should be initialized. In other words, this init event, notice that it has 0 delay, whereas for the arrival event is going to typically have a positive delay. So the arrival event is going to happen sometime in the future. These are all happening at time 0. So at time 0, this is spinning and spinning, and each time it happens, it's going to initialize the next item. So see, init I is going to set Si equal to Ki, that is the number of available servers at station I is going to be the total number of servers at station I, and Q sub I, the number in the queue at station I, is going to be initialized to 0. So this is how we initialize a state variables that are arrays. So this is the pattern that should be used. So when we break it down, those are all the pieces. But here's the thing. If you look at this, and we've kind of encountered this a little bit before, that you should start to be noticing patterns. Like there are 3 patterns here. In fact, this is one, this for loop. Here's another pattern right here that we've seen a lot, that this event that gets scheduled with a certain delay and just keeps scheduling itself. And then this other piece here, this is yet another pattern that we see kind of recurring. The problem is that when we look at this all kind of glommed together, as you can imagine, if we have a complex event graph, as we add more and more events, it starts to look more and more like a plate of spaghetti or ramen. Or, in other words, the more, as this gets more and more complex and we have more and more events that are taking place, it gets more and more unwieldy and more difficult to manage, more and more difficult to debug, more and more difficult to just verify and validate. So the idea now is to take the concept of an event graph and to break it up into components. And the motivation for that is noticing that there are certain recurring patterns that lend themselves to kind of isolating. And that's what this sim event listener thing is about. So the question comes up is that how can we connect these different, like if I were to break this up into different pieces, such as the arrival piece being separate from all of this, how can we make sure that they actually connect? And that's what this sim event listener idea is. And what it does is it operates with the events. So a sim event listener, as the name suggests, is hearing events. So when I have, these are like, each inside of these would be 2 different event graphs. So in the source, I have events that are just kind of occurring. And every time an event in the source occurs, after, what does it mean to occur? It means it performs its state transition and it schedules whatever events that are dictated. When it's finished, then it dispatches that event, that same SIM event, to all of its listeners. In this case, we only have one, but you can have as many as you want. And that listener, if it has that same event, then it processes it as if it had been scheduled. Let's look at an example of this. Okay, so here are two components. And again, these are obviously not complete, but so let's say this source event has an event A, and that event A is going to schedule B and C. And at some point, let's say, at some point B is going to occur. So when B occurs here, after it's done, it gets dispatched to its listener. And this listener says, oh, I've got a B. And so this in turn will schedule the event D in this component. At some point, the event C will occur. And that gets dispatched, but this listener, it hears the C. It says, oh, I just heard the event C, but I don't have a C, so I'm just going to ignore it. And also, the other thing is that event A is not scheduled by anything in the source component here. So it will not get dispatched. So the idea is that events B and C will be heard. Only event B will be responded to because it has this. Event A will not be dispatched because for a variety of reasons, if I hear an event, I don't send that to my listeners. Okay, so here's how that works. So event A occurs at some point, and it schedules B and C. Okay, when event B occurs, the listener hears it, and it will schedule D. All right, let's look at a more concrete example. So let's say, for whatever reason, I have two arrival processes, and for whatever reason, I want to just count the total number of arrivals that are in all of them, and I don't care which one they came from. Okay, so I already have an arrival process in hand. I know what that is. I mean, in order to do this task, I'm going to write an arrival listener that's going to have a state variable H, which is the number of heard events, arrival events. So its run event is just going to simply initialize that to 0. And every time I hear an arrival, I'm going to increment the number of arrivals I've heard by 1. So every time this arrival process has an arrival occur, it'll be heard by this. And every time this one has an arrival, it'll also be heard by this. Okay, and that example is in the code, and it's called arrival listener. So let's take a look at this. It's, again, a very, very small component, but again, it matches. It should match what that event is. In fact, let me try to share the whole screen just so we can kind of compare them here a little bit. All right, so where are, let's show. Darn it. Let's put you over here and make you just a little bit smaller so we can. Okay, So this class is implementing what's just this one piece right here. Okay, so H is going to be the number heard. Okay, and it is protected because it is a state variable. So state variables have a getter but no setter. Here's the run event. The run event is implemented. The initialization is in the reset method for reasons that we'll eventually explain. And then the run is simply fires the property change. That's all it does. Notice it does not schedule anything. In fact, none of this component is going to schedule anything at all. Okay, but here's the it has a do arrival method, which matches the arrival event. And the state transition is the number heard incremented by 1. So just as with the other state variables, I get the old value, I increment it by 1 and fire the property change. That's really all there is to it. So here's how we're going to test that. Here's what that's going to look like. So here I said 2 arrival processes. So here are 2 arrival processes. The first one, I'm going to have an exponential inter-arrival time. The second, I'm going to have a gamma distribution for the inter-arrival times. So here's arrival process 1, arrival process 2. Here I instantiate the arrival listener. Okay. All right, now here's where I connect these. See these connections here are the listening connections. And the way I do it, it's a little bit backwards, and sometimes I forget this. So arrival process, add sim event listener, arrival listener. So that's what this listening edge does. And then arrival process 2, add sim event listener, arrival listener. So that should look somewhat familiar. Again, going back to the action listener, that's how we added an action listener to a button. So we had an instance of the J button, we said add action listener, and then gave it the instance of the action listener. Likewise, with the simple property dumper, we add just as we're doing here. So we instantiate a simple property dumper and we add a property change listener, and I'm adding a property change listener to each one of these guys. And then again, you always want to kind of, when you're running it like this, we want to print it out. We're going to run it in verbose mode, say for 20 time units, and then print out what our results are. So let's run that. And see what that's all about. Okay, so first, here are our 3 sim entity components. Again, here's an arrival process. Here's with the exponential. Here's a second arrival process with the gamma inter-arrival times. And here's our arrival listener. And then notice that it doesn't have any parameters. And that's just the way it was designed. Okay, so what's happening is now just one thing that I did was when I instantiated my simple property dumper, I gave it the true, I said true. And what that does is that lists the source of the property change because we have 3 components that are firing property changes. Okay, so the run for arrival process 1, 0 arrivals. The run for arrival process 2, 0 arrivals. The run for arrival listener, and that has number 0 heard so far, okay? But the arrival process 1 scheduled an arrival at this time, 0.84 something, and arrival process 2 scheduled an arrival at 0.9 something. So what this indicates is that this arrival process is scheduling this arrival, And the second arrival process is scheduling this arrival. So let's see what happens. So here, what's the next thing to happen? Well, at time 8472, arrival for arrival process 1 occurs. Now that there's one arrival for arrival process 1, and the number heard for the listener is now 1. And then another, see what happened? Like the next arrival for arrival process 1 snuck in first. So that's the one that happened next. So now it has 2 arrivals, and the arrival listener has heard 2. All right, then finally, the second arrival process gets its arrival, so it has 1, but now the number heard has gone from 2 to 3, etc. So every time an arrival event happens for one of the arrival processes, its number gets incremented, and the number heard gets incremented from it. Notice how they're different. So the number heard in this particular case, the arrival listener, is counting all of the arrival events for every component. And it just keeps going like that. And then at the end, we just sort of say the arrival process 1 had 5 arrivals, the second one had 9 arrivals, and the total was 19. And so at least it's doing the calculations correctly. So that's always good to know. Okay, so that's sim event listening in action, again, for an admittedly somewhat arbitrary and classroom-like example, but that should illustrate to you the idea that when an event happens in one component, it can get heard in another component. And so we can exploit that to have a more componentized version of our multiple server queue. I call it the simple server component. And the motivation for that was noticing, just as we saw here in the transfer line, that that this arrival piece is, tends to be a recurring type of thing. And then actually this kind of pattern is like the multiple server queue pattern. Okay, so if we go all the way down, so the simple server component just captures the server part of the model. In other words, it puts the arrivals outside in a separate one. So it omits the specific arrival sequence. And so in order to work, it has to listen to another component that schedules arrival events, such as the arrival process. But the flexibility it gives us is that any component that schedules arrival events can now be used to drive this this component. And in particular, we could have a situation like this where there might be 2 different arrival process streams. There might be 2 different mechanisms that produce arrivals to the system. And so we can model them as 2 different unique arrival processes, but then have it be heard by the same server component if we want. We're not going to do that yet, but but we will. So let's just look at this, what this component looks like. Okay, just like with a full event graph model, we have the same elements: parameters, state variables, and an event graph. So our parameters now, notice we only have 2. We have the service times and the number of servers, but we don't have the inter-arrival time. So this is simpler than the full-blown multiple server queue component because it leaves those out. Now our state variables, we'll define them as before for Q and S, and then I'll add N for the total number of service completions. And we'll call that that will be initialized to 0. Okay, so this is how we're going to have our state variables. And now the see, now the component is a lot simpler. See, first of all, we have a run event that doesn't schedule anything, but it only initializes our state variables. Everything else is everything else is more or less the same. So we have our arrival event that increments Q. If we have an available server, we start service, schedule start service. That decrements S and Q. Start service schedules end service. End service now increments S and then increments the number. N was the number served. And so we're only going to count that when we get an end service event. So you see how much simpler this is than even the multiple server queue piece. And the simpler we can make our components and still have them be doing what we want, the better. In other words, this has fewer things to debug. Now, the cost of that is, notice, if this is the only component that I have, what's going to happen is the run event is going to occur, and then the simulation is going to end because it doesn't it doesn't schedule anything. Okay, so how can we make this live? We make it live by instantiating an arrival process and then instantiating our simple server and then having the simple server listen to the arrival process. And this is what it looks like. So here's our arrival process. Again, we formulated that as our as our hello world of event graphs. We've implemented that in SimKit, and having implemented it, we now have it. We can reuse that. We can just reuse instances of that. Notice that in the example I just gave, the only new component I had to write was that arrival listener piece. I could reuse the arrival process that I'd already written, just to create new instances of it. Okay, I see a question. Yeah. Hopefully I'll survive to the end of the class. Just all of a sudden something started tickling my throat. So, and I've been fully vaccinated, so it's not. So you're not going to be able to catch anything through the computer. Okay, so here's our server component. Again, this is just what we had before. Come on. Okay, just like that. Okay, so here's whenever these arrival events occur, they're going to get dispatched to the server component that is going to say, oh, I have an arrival event. And so it will execute that arrival event and then schedule the start service and then carry on from there. Another thing, and I did this deliberately, is the fact that notice that there's a state variable called n in the arrival process, and there's a state variable called n in the server component. Because these are separate classes and a state variable is implemented as an instance variable, the fact that they have the same name here in the event graph does not matter at all. Now in the implementation, okay, we already have, this is the number of arrivals. In the implementation, I would call this number served, so there wouldn't be any ambiguity about that. But for the event graph model, it is absolutely 100% okay to have the same variable name in different components that mean different things. These mean totally different things. They have nothing to do with each other. Remember in the Java class, I ranted about encapsulation, and that's what's going on here. The arrival process encapsulates its state variable, the number of arrivals. And the fact that I'm calling it n, and over here, this n is the number served. This is totally encapsulated by the server component. So they are completely different, and there's no ambiguity. Okay, so that's it for today. If you've pulled my code, as I was, if you have trouble with that, let me know and I can help you do it. It's basically the same as we did in the Java class. So the first time you want to clone my GitLab, and then after that, to update it, you do a pull on mine, and just make sure that you don't pull my stuff into yours or your stuff into mine. So you can, and the way I've set it up is you can pull my code, but you can't push it. So that's what that is. In that, there's an implementation of that inventory model that I did in the first part of today's class. I'm not going to go over that explicitly, but it would be useful just to take a look at that and compare that to the event graph model and see what that relationship is like. So tomorrow we're gonna continue talking about simulation components and this listening thing. And in the next computer assignment, which will be posted this afternoon, we will be implementing the what I just did for the. In other words, instead of implementing the full-blown multiple server queue, I'm going to have you write the server, the simple server, and then run it as I run it like this. In other words, you've already done the arrival process. You're going to get to reuse that and just simply write the server component piece.